Real pleasure to be here. And I want to start as well by thanking CART. The support that you're giving me to do this work is really just going to change the trajectory of the work that I'm able to do. And as you'll hear from what I'm about to talk about, I'm all about tracking trajectories. So I also want to say a word just in memory of Dr. Trojanowski, who's not someone that I personally know, but who's touched the lives of a lot of the people around me, and is one of the giants whose shoulders I stand on. I work with people who've known him for decades, and all I've ever heard about him was the most wonderful things, that he was a really kind person, a good scientist, and was a helpful colleague. So with that, I also maybe should say a little bit about my why, and maybe it should be obvious with my parents here as well. Alzheimer's disease is a very personal thing for me. When I was a postdoc, I wasn't studying Alzheimer's disease, but my grandmother started to show signs of dementia. And I can still remember a lot of the ways that it impacted her, it impacted my family. And well, I'll get a little too emotional if I talk on that too much, but it's something that I would really love to see me end up. So I'll tell you a bit about the work that I've been doing since I joined MGH in Harvard. And it really has to do with pictures like this. And something that I learned from a lot of the work that I did previously is a lot of our understanding of diseases really comes down to what we can see, how we can interpret it, how we can look at it. Here are two MRI images. One taken on the left is a brain that has Alzheimer's disease, and the one on the right is a healthy brain. If you were to just take an MRI image and you were to stick it on a screen, they kind of look like a couple of indecipherable blobs. But if instead you took some of the computers that we have now and you start to make surfaces and you put lights on them, you can see a lot of really incredible differences in the brain that you weren't really able to see before. You can see this brain on the left is shriveled, it's shrunken, and a lot of the questions that we're able to ask about Alzheimer's disease really comes down to our ability to see these things. A lot of the ways we can monitor the effectiveness of treatments has to do with whether or not we can see what's happening. So, historically, there's been a lot of effort to improve the ways that we can look at the brain and look at what's happening, that we can look at people and see what's happening earlier and earlier and track how these changes are affecting them. You end up with archetypal sequences of changes, things like this, where people will say that something changes first, followed by another, followed by another. But what we end up seeing in people is, despite this kind of sequence of changes, there is still this substantial variability in the trajectory of dementia. And we don't have a great way of understanding why it is that. So what we see is a great variability in the trajectory of Alzheimer's disease. And it becomes very difficult to try and understand when you're talking to a patient what is going to happen to them in the next year, in the next 5 years, in the next 10 years. There are times when I'll receive a call from my parents and they'll say that one of their friends has recently been diagnosed with MCI and they don't know what that means. And they want to know, how should they plan the rest of their life? But their doctors are reluctant to tell them how many years they have of normal cognition. Is it 5 years? Is it 10 years? Do they need to start worrying about the next year? And the plot on the last slide really shows you one of the reasons that there's a lot of reluctance for doctors to tell a patient what's going to happen next is there's such a huge variability in what we see in people. And while there are a lot of new methods that are helping us understand what's happening in people while they're alive, historically, a lot of our information has come from people who've already passed. You'll see pictures like this, where they'll try to take images of a human brain from a bunch of different people. And they'll try to come up with a timeline or some kind of staging and say, oh, well, there's a little bit here in stage 1, and then you can see more in stage 2 and stage 3, and then by the time you reach stage 6, there's just so much everywhere. So obviously a person will go along that kind of trajectory. Next slide. But the way that I think about this is it's really like trying to understand a sports game by looking at the final few seconds. And if you were to take these are just a few screenshots of ones I could find on YouTube, and you were trying to look at this and tell what game this was, and how it was played, and what was happening, you might think, okay, well, football's where a bunch of guys dress up and hug each other. Next slide. There are new methods that get developed that really let us observe living people. We can start watching the game, but they don't necessarily give us the resolution that we want to watch the full game. So you'll see snapshots over time. And if I take an image every 25 minutes from this game, you'll see, okay, there are a couple where they're actually playing football. But only 8% of the runtime of this football game involved people playing football. An average play, I read, was 4 seconds long. In the case of a person and their life, what percent of their life involved their brain degenerating? What's the time scale? What are the events that happen? And are the technologies that we have really giving us access to those events? Next slide. So, as you can imagine, these observations will strongly impact the hypotheses that we can develop and test. From those images, you'll see things like, okay, there are 22 people on a green field, there's 1 ball, there's a giant fan for some reason. Based on these observations, you can see at the end of the game, it stops. A bunch of people flood the field. So you might come up with this hypothesis that the way we need to treat Alzheimer's disease, the way we need to stop the football game, is by flooding the field with a bunch of people. And it can be really hard if we don't have good methods to observe what's going on, to understand what it is we actually want to treat, or whether the treatments we have are effective. Next slide. So from these, we'll often try to make mouse models that are based on what we see in study. So here we recreated what we saw. Is this mouse also going to get brain damage? Well, next slide. We have this new set of methodology over the past few years, ranging from things like amyloid PET and tau PET, different types of MRIs, and now some really wonderful new blood tests that came out in the last year that are changing the way that we understand this disease. They're changing our ability to classify these diseases, how we perceive it. Some of the perception that people will often have is that neurodegenerative diseases have a debilitating outcome in the vast majority of cases, but what we're seeing is that's not true. That they're really a spectrum of conditions with heterogeneous prognoses, including many that are benign. And what we have to ask when we're trying to categorize these things, when we're trying to understand what's happening in people, is, are we actually measuring the right things? Next slide. So you'll see from this past year, with these new methods of observing the brain, there are, in blue, a lot of people who meet certain biological definitions of Alzheimer's disease that end up with no cognitive impairment through their entire life. But they would have been invisible if we were only diagnosing people that came in with clinical symptoms. Understanding that disconnect, understanding why it is that some people develop the disease, what happens to them once they do, is going to be very important for any of these treatments, including the kinds that Viv was just mentioning. Next slide. So in my lab, my goal is really trying to develop new ways that can monitor these changes caused by Alzheimer's disease and see if we can find ways to inform trajectory and treatment. In one case, which I won't talk in detail about today, we'll look at functional changes with brain codes that we put into the brain to recover, to uncover functional changes in neurons and their networks over long periods of time. And what I'll talk about today are some really wonderful insights that we've had from looking at structural changes and starting to test these questions about what it is that might be causing neurons to die. Next slide. So tau tangles, which you can see here on this image, are these weird little formations in white. And neurons, in red, you can see get enveloped, although the tangles themselves are usually inside the neurons. But you can see these kinds of weird structures that are all throughout even just this small section of the brain. One of the things that we'll often hypothesize when we see something that's weird in a brain is obviously that weird thing is what's causing all of the problems that we think are there. So if we see something like that, there will be a lot of treatments that are focused on trying to remove those things, especially in the case of tau tangles, where they correlate very well with neurodegeneration and cognitive dysfunction. We can develop mice models that also form these kinds of tangles. You can see here from 3 months to 6 months to 9 months to 12 months and 24 months in white. Those are those same aggregates forming all across this mouse's brain. So the experiment that we set up initially was putting a little window above the mouse's brain, putting different compounds into its brain that flow in a way that let us track both the formation of these tangles and the loss of neurons. And this ended up being a very challenging problem. If you push forward, you can see a little video on the left. So if we image this, you can see there are blood vessels in red, and we see the neurons in purple, and some of the tangles in white. So we took these, and you can imagine it kind of like taking a constellation pattern from the sky. And we tried to take this image as frequently as we could, and then match these constellations on top of one another. So we could identify which neurons persisted from week to week, and then try to figure out which ones were being lost. And you can see from looking at this, this is the change across 4 weeks. And just from the outset, it doesn't really look like a lot's changing. But if you think about what's happening in a brain, it doesn't just suddenly degenerate. So it's kind of like a needle in a haystack problem. Which of these neurons are disappearing? Which of these tangles are forming? Gives us a lot of really interesting insight into this disease. So now what we're able to see, of about 1,500 neurons that we observed, 178 of them were lost. And of these, only 6 of them had this neurofibrillary tangle. So the neurons with tangles were actually 3 times more likely to survive than the ones without it. This turns a lot of assumptions about the disease on its head. This assumption that this protein that we're seeing might be a problem, rather than a solution that your brain is coming up with to try and protect itself. I kind of view this as what I call the dumpster hypothesis, or one of my colleagues in my lab calls the hoarder hypothesis. Imagine you have someone who's just got a really disastrously messy house. You won't necessarily see it from the outside. But if they order a dumpster, put it in their driveway, and you see them collecting all of their trash there, you might drive by and think, what's going on? Why do they have all of that junk? But their house is a lot more livable now. So with this in mind, if tangles are not what lets us predict that a neuron is going to die, what might? So we decided to try and look back in time, look at the neurons that died, and see if we could find features that helped us predict that they were going to be lost soon. And what we saw was that the neurons that were dying typically pushed away their neighbors for at least a couple of weeks before they died. And then after that neuron was lost, the other neurons moved back into the space that it took. we don't know why this is, and I would say this is at the core of the proposal that CART is helping to fund. This idea that if we're able to find neurons that we can see are going to die in the future, maybe we can do something about it. And we can see if we identify in the brain all of these neurons, we see thousands of them. And after identifying them, we observe them, about 50% of the neurons that show this characteristic die within 1 week. And the likelihood that they die is increased based on how far apart they push their neighbors. So that was all data from mice. Now we wanted to try and establish, does this happen in people? And we took similar types of dyes to label similar types of things. Here you can see in green we have neurons, in white we have tangles. And we started to use these advanced imaging technologies that give us the ability to image hundreds of thousands or millions of neurons across the brain. And then we can take this and use machine learning-based segmentation to identify their locations, identify whether or not they have tangles. And we find that neurons with this characteristic are much more likely to appear in human brains that have Alzheimer's disease. So, in summary, we're able to do these kinds of longitudinal observations of neurons. We can get this extraordinary insight into the effects of this pathology, but there's a lot of questions we have about how this works and why it works. If a neuron's death isn't immediate, it really poses this question, maybe we can do something about it. And if the other neurons around it can tell that a neuron is going to die in the near future, there must be some kind of signature, something that we can latch onto so that we would be able to tell this as well, and potentially develop new methods similar to the MRI or PET scan methods that exist that let us measure the abundance of degeneration happening in the moment rather than waiting for sufficient brain degeneration to happen where parts of your brain have shrunk, where clinical symptoms start to manifest. So thanks to CART, we've started to put together what I think is a really wonderful way to address these questions. And our goal is to understand what's going on here. We're going to try to define which populations of neurons show these changes, see that it happens in brain regions that we think are vulnerable, see how it changes with age, see how it changes with co-pathologies. And our real hope is not only will we be able to make new ways for observing neurons that are imminently dying in a living human brain, but also use these as a launching point to test new interventions where we can stop what it is that's causing these neurons to die, rather than focusing on the pathology and focusing on what's going wrong, see if we can cut the chain closer to the source of what we want to do. So here I just wanted to show you a couple of pretty images for how we can do this. On the bottom left, you can see that is an entire mouse brain. And we're able to label it with a bunch of different things that gives us this really incredible view in the structure of the brain. And on the bottom right, you can see a similarly sized piece of the human brain. And with both of these together, we can also make sure that what we're doing in mice translates to what we're trying to look at in people, and make sure we're not making the mistake of dressing a mouse up in a costume and assuming that it can play football. And we've also developed some wonderful chemical technologies that let us label the proteins both inside and outside these cells that we can extract and use a technology called mass spectrometry on. So we can try to figure out what it is that's underlying these changes that we can start to target for treatments. So with that, I would like to, again, thank all of you at CART for supporting this project, supporting me, and the people in my lab, Regina, Victor, Dina, and Hao Young, as well as a lot of the people who've helped me along this way, especially Brad Hyman and Rachel Bennett, who were absolutely essential in both teaching me about how to approach Alzheimer's disease and making sure that these projects move forward. Thank you.